We are moving on now to exponents and scientific notation. So this is going to be your section P.2. So still in the preview, prerequisite sections. We're going to go over rules of exponents. As you see several more here. We're going to use these to help us simplify exponential expressions. And then our very last bit on exponents is going to be doing scientific notations. We're going to learn to transfer something into scientific notation and then back. So going back over the basics here, you probably know this already, but exponents are an expression of multiplication. So if I say I have b to the power of n, that means that b is multiplied to itself n times. So if I have 2 to the power of 5, well, that means I'm going to have that 2 is multiplied to itself 5 times. And we know what this is, so 2 times 2 is 4, times another 2 is 8, times another one is 16, times another one is 32. We call b the base. So 2 would be the base. And we call n the exponent. So 5 is the exponent. And as you see here, I do have another example. So if I had 3 to the 7th, that means I have 3 is multiplied to itself 1, 2, 3, 4, 5, 6, 7 times. And the base is once again going to be that 3. And your exponent is going to be that 7. So first things first is we're going to start with what is called the product rule. So when multiplying exponential expressions with the same base, we are going to add the exponents. So they have to have the same base. That's what is very important here. So if I have b to the power of n times b to the power of n, then that will equal b to the power of m plus n. So I have an example down here. I'll do one more here. So if I had 3 to the power of 2 and I had 3 to the power of 4, well, that means I have 3 is multiplied 2 times. Then this 3 is multiplied to itself 4 times. And what we have here is 3 times 3 times 3 times 3 times 3. So I lost count. 1, 2, 3, 4, 5. Need 2 more. 6, 7. 1, 2, 3, 4, 5, 6. One extra here. So we end up having 3, 1, 2, 3, 4, 5, 6 times. And that is just 3 to the 6. So I could have just added those exponents. Same thing here. So if I have 2 to the 3rd and 2 to the 5th, then I have 3 2s. I have 5 2s. Altogether, that's going to give me 8 2s that are being multiplied together. Okay. So keep in mind that if you're multiplying two numbers of the same base, you can add the exponents. We're going to have something that's going to look similar to this that I find students get confused with, but this is multiplying two numbers with the same base, or two exponents with the same base. So here, we want to multiply expression using product rule. So what we can do is we have that commutative property with multiplication. So I have 4 times x to the 3rd times y to the 4th. All that is multiplied to 10 times x squared times y to the 6th. So commutative property means I could put the 4 and the 10 next to each other, multiply them. The x's can go next to each other. And the y's can go next to each other. So 4 times 10 is just going to be 40. I have here x to the 3rd and x to the 2nd power, same base, add the powers. That means altogether I'm going to end up with 5 x's. Y, I'm going to have 4 y's here and then 6 y's here. So same base, we add the powers. So just as long as you're multiplying the same base, this is going to be just 40 times x to the 5th times y to the 10th. And this is going to be the simplified form. the simplified form of this expression here. Quotient rule, very similar to product rule. So when dividing exponential expressions with the same non-zero base, subtract the exponent in the denominator from the exponent in the numerator. We use this difference as the component for the common base. So basically, if I have b, so same base, b and b to the power of m, but dividing by p to the power of n, that is equal to b to the power of m minus n. So whatever is your numerator, that is the first one. Whatever is your denominator, that's the second number here. So if I had 2 to the power of 3, and that was over, say, 2 to the power of 5, just to show you how, well, let's pick a different number. Almost going to be a little too much extra rules there. Let's say we have 2 to the power of 7, and then we have 2 to the power of 2. That means we're going to have 2 times 2 times 2 times 2 times 2 times 2, 2, 3, 4, yep, times 2 on top. And on bottom, we have 2 times 2. So because it's all multiplication, this 2 and this 2 will cancel each other out. One's gone. This one cancel each other out. That's gone. And all I'm left with is 2 multiplied to itself 5 times. So as you see, this could have been gotten by simply going, okay, I have 2 to the 7th. I have 2 to the 2nd power. I'm going to subtract my powers. So I got another example down here. If I have a 5 to the 3rd and 5 to the 2nd power, same thing. Same factor on top and bottom can cancel out. I'm just left with 3 times. So I could have just taken 5 and subtracted. Okay, so we're going to use the quotient rule here. So we have 27x to the power of 14 times y to the power of 8, all this divided by 3 times x to the power of 3, y to the power of 5. So you can do this in little sections here. So, because it's all multiplication, so 27 divided by 3, well, that's just 9. Then we're going to have the x to the 14 divided by x to the 3rd. Well, that's just x to the 14 minus 3. So remember, numerator exponent first, denominator exponent second. Then if we look at y, we've got y to the 8th and y to the 5th. So y to the 8th is on top and 5 is on the bottom. We're just going to have 9 times x to the 11, y times 3, or y to the power 3. Okay, so take a moment, do worksheet problem number 1 and work on these two. So both of these are going to use a combination of product and quotient rule. So just use it to simplify these. So you just have one coefficient and then one variable to a power. All right, so hopefully you had some time there. So for A here, we have 39 divided by 13, which is going to leave us with 3. We have A to the 7, and we have A to the 6. So we're going to have A to the 6 minus 7. B, as you see, there's no other B here. We're just going to have B to the 3rd. And then with the C's, we see we have C to the 5th minus C to the 5th. Or you could have said, just cancel out, and I don't have a C there at all. So if you chose that, that is fine. So we're going to have 3A, because it's A to the 7th minus B, so that's A to the 1, B to the 3rd. And we know we don't need to keep that exponent of 1. So we'll just say 3 times A times B cubed. So here we have 9 over 12. This is a little different. So the 9 over the 12, we just need to simplify that down. So both of these are divisible by 3. So that's just going to simplify down to 3 over 4. We have 3 over 4, and we see we have an x. There isn't another x. We have z. There is another z. So we have z to the 6 minus z squared. And then we have 1y. We have y squared. So if it doesn't have a friend, nothing changes. It just stays where it is. So we're just going to have 3x squared z to the 4th 4y squared. Okay. This kind of takes us back to the last problem a little bit here. Might go back to it here in just a second, but if b is a real number other than 0, then we're going to say that b to the power of 0 is 1. If the base is 0, then we say 0 to the power of 0 is undefined. So as an example here, if I had 3 to the power of 0, as you see down here as an example, what that means is that I have 3, and I just have to find a way to write this exponent as 0. So I just say 1 minus 1 because that's also 0. If I go backwards with that, what that means is that I had a 3 to the power of 1 over a 3 to the power of 1, correct? Because then once I go back this way, that's just 3, 1 minus 1. Well, we know that if I have this is just 3 over 3, that's just equal to 1. So when you have a power of 0, it's basically saying that you have a quotient of the number over itself. We end up with 0. Or sorry, we end up with 1. Looking at 0, as I said that. If I have 0 to the power of 0, well, that means I have 0 to the of 1 minus 1, like I did before. That turns into the same thing. That means I have 0 to the power of 1 and 0 to the power of 1. But we cannot divide by 0. Anything divided by 0 anything divided by 0 is in itself undefined. So it doesn't matter if it's 5 divided by 0 or 0 divided by 0. If you divide by 0, it is undefined. So 0 to the power of 0 is considered undefined. Negative exponents, this is going to help us get into one of our other rules here. If b is any real number other than 0 and n is a natural number, then b to the power of negative n is just 1 over b to n. If I have b to the n and I want to rewrite that so it has a negative exponent, well, that's just equal to 1 over b to the power of negative n. So if I have 2 to the power of negative 1, I can write that as 2 over 1 or 1/2. So we frequently use that negative 1 to write something as a fraction or to express that as a fraction. If I have 5 to the power of negative 3, that is the same as saying I have 1 over 5 to the power of 3. If I had 1 over 2 to the negative 3, well, that I can rewrite because if I have this negative here, as we saw here, I can rewrite that as 2 to the power of 3. So there are some good uses to have in these negative exponents. Like I said, sometimes we use them to actually express that something is a fraction. We just like to do it with a exponent instead. I'm sorry, my stuff is getting in the way here. Then you use the negative exponent rule to write each expression with a positive exponent. So I have 5 to the power of negative 2. That would just be 1 over 5 to the power of 2. Now I'm going to make it a little more tricky. If I have 3 times x to the power of negative 6 and y to the power of 4, this is the only thing that actually has a flip to it. So this is just 3 times 1 to x to the 6 to make that a positive exponent. So part of the rules of simplifying is that we do not like to have negative exponents. So this rule helps us get rid of these negative exponents. And this is the equivalent of saying that I just have 3 y to the 4 over x to the 6. So one of the ways to kind of think about this is that what we're happening here is that when we have a negative exponent, it's going to move its place. So if it's in the numerator, it moves into the denominator. If it's already in the denominator and it's a negative exponent, then we move it in the numerator to turn it into a positive exponent. So thinking about it this way will help kind of move these around a little bit. All right. So we're going to use product rule, quotient rule, and exponent rule, whatever shows up here. We may only need to use one or two of these. You want to take A and B, and we want to simplify these as much as possible. So that means we do not want negative exponents. If we can combine something down to it's only the variable and an exponent, we want to try to do that. And if we have anything like it's a fraction that can be simplified, simplify that fraction. Try to simplify these as much as you can, and we'll come back and work on these. Pause the video and work on these for a second. All right, so with A, we got 5 over 7. This does not simplify in any way. So we're going to be left with 5 on top and 7 on the bottom. So we have an A. We have A to the power of 3. And then we have A to the power of 6 on the bottom. So because it's a quotient, we keep the 3 and then we subtract the 6. If we look at C there, we have C to the power of 5. And then we have a C down here. So this one looks like you don't see an exponent. Remember, it has an invisible 1 on it. So this is 5 minus 1. Now B, we'll keep B down here because B doesn't have any friends to combine with. That's going to give me 5, A to the negative 3, C to the 4, over 7, B to the negative 3. Now for the next part, we're just going to turn negative exponents into positive exponents. So we're going to have 5, and we're going to have 7 down here. So this A to the negative 3, it's in the numerator, so we just pop it down to the denominator. And now that negative 3 turns to positive 3. C doesn't need to go anywhere because C is perfectly fine. It stays up here. Now if we go to B, we got B to the negative 3, and we want to turn that to a positive exponent. We're going to flip it up to the top. And that's going to be B, now the positive 3. Just to make a note here, if you've written, your answer may have looked like this instead. That is also okay. There's no rule that's saying that B has to come before C or anything like that. So this was also an acceptable answer. All right, so for B here, we got 24 divided by 8. So we want to simplify this. So 24 divided by 8. Both of these are well, actually, sorry, I was gonna say both are divisible by 4, but 24 is divisible by 8. So 24 divided by 8 is just 3. So what you could do is you're gonna put the 3 on top, and then we have x. We don't have another x, so we just have x squared. Then we have z to the power of -6. And we have another z though. We got this one on the bottom. Remember, we subtract whatever we have down here. So we have a 2, so we're going to have -6 minus 2. And then the y is the only thing we have left, and we had y to the -2. So we have 3 x squared, z to the -8, y to the -2. So that's going to be 3 x squared. This y has the negative exponent, so I can stick that on top so that -2 turns to +2. That z got a negative exponent, so if I stick it on the bottom, I can change that to z to a +8. Some of you may have done this a little differently, so I'm not going to do this with A, but I'll do it with B. Alternatively, what you could have done is this as well. So you would have had the 24, I was trying to remember it so it wasn't sticking in the weird spot, 24x squared, b to the -6. So there's no rule saying you have to do rules of exponents in any particular order. I could have first moved the exponents so that they went from negative exponents to positive. So I could have taken this and went, oh, well, that's just 24 x squared. And then I could have taken this y and stuck it up here. Instead of having y to the -2, I could just pop it on top and have y to the +2. And even though I had a z to the power of 2 here, I can take in this z to the -6 and stuck it down here so it goes from negative to positive and rewritten it this way. Oops, forgot my 8. So 24 divided by 8 is still 3. Now we have x squared, y squared, and we have z to the power of 2 times z to the power of 6. So z to the power of 2 plus 6. So we had 3 x squared, y squared divided by z to the 8. Like I said, that's an alternate way to do it. There's no right way or wrong way here. As long as you follow the rules of exponents, it should work. It doesn't have to be followed in a particular order. All right, next we have the power rule. So this one gets a little confused with the product rule. So this is powers to powers. So when an exponential expression is raised to a power, so we already have an exponent and then we raise it to a power again, we multiply the exponents. So if I had b to the power of m, and then I raise that all to the power of n, then that is b to the power of m times n. So if I had, say, 2 to the power of, sorry, 5 to the power of 2, and I raised that to the power of 3, what that means is that I have 5 to the power of 2 3 times, and each one of these is just 5 times 5, so that's 5 times 5, 5 times 5, 5 times 5. And as you can see, we end up with 5 multiplied together 6 times. So this would have been the same as just saying I have 5 to the power of 2 times 3. As you see, a similar thing down here, except the 3's on the inside and the 2's on the outside. So I got b to the power 3, b to the power 3, expand it, still going to work the same way. So we want to simplify each expression using power rule. We have 3 to the power of 3 to the power of 2. I think we've seen this one enough times. That is going to be 3 times 2. So 3 to the power of 6. Here we have negative powers. We have b to the power of negative 4. And then we raise, or sorry, negative 3, and then we raise that to the power of negative 4. So we just multiply the power of negative 3 times the power of negative 4, and that becomes b to the power of 12. So you can have those negative exponents in there. All right, so from there, we're going to go from products to powers rule. So this one is saying that if I have two different numbers multiplied together, and that is all raised to a power, I can distribute that power. So if I had, say, 2 times 3, and I raised that to the power of 4, that means I have 2 times 3, 2 times 3, 2 times 3, and 2 times 3. So I have that 4 times. So that's 2 times 3 times 2 times 3 times 2 times 3 times 2 times 3. So we have 2 4 times, and we have 3 4 times. So I could just distributed the power. Same thing here. So I have 3x to the power of 5. That's 3x times 3x times 3x times 3x times 3x. Put all the 3's together, put all the x's together, because we can do this commutative property. That is 3 to the power of 5 and x to the power of 5. So we want to use the product rule here. So we have negative 4x to the power of 3. Well, that's going to be negative 4 to the power of 3 times x to the power of 3. So technically, to simplify this, I can get rid of this power here, because I just know that as negative 4 times negative 4 times negative 4. So the negative 4 times the negative 4 is going to be 16 times negative 4. And now we're going to have 16 times 4. Or sorry, 16 times negative 4. That is going to be negative 64x cubed. Another part of our simplifying is that if we actually have a number raised to a power, we want to write out what that number would be within reason. Sometimes if it's really big, like I think 3 to the power of 9 is really huge. Let me double check that. Yeah, so if you take like 3 and you made it like to the power of 20 or something like that, then you might just want to leave it as a power. But if it's something that's reasonable you can write down, then you want to write it as a number, because we don't like to have more power sitting around or exponents than is necessary. Quotient rule for exponents. So it's kind of like the power rule or the product rule. If I have a over n and I raise that, sorry, a over b and I raise that to n, then that distributes as well. So I get a to the n and b to the n. So if I had 2/3 and I raised that to the power of 5, well, that is 2/3 times 2/3 times 2/3 times 2/3 times 2/3. So that's just 2 times 2 times 2 times 2 times 2 over 3 times 3 times 3 times 3 times 3, or which is just 2 to the power of 5 over 3 to the power of 5. Like I said, another example, x over 2 to the power 3 is x over 2 times x over 2 over x over 2, which means that I have, if I combine that, is x times x times x over 2 times 2 times 2, x cubed over 2 cubed. I think I had a power missing here. Okay. Sometimes when I turn these into PDFs, things disappear. Let us put a power of negative 2 on this. So negative, I was trying to figure out what it was be. I think it was supposed to be just negative 2 over y. So this negative out here, you can stick it on the top or bottom, so you can make that negative 2 over y to the power of 2, which means we have a negative 2 squared over y squared. We end up with a negative 2 times negative 2, which is just going to be 4 over y squared. And then we have x to the 5th over 3 to the power of 3. Well, according to my rule, that's x to the 5th raised to the power of 3 over 3 to the power of 3. So we have that rule about a power raised to a power, so that is just x to the 5th times 3. And 3 to the 3 is just 27. So to simplify, this would be x to the 15 over 27. Sorry about that glitch on the slide there. We want to use power product rules, quotient rule, all of our rules that we have here, and simplify the following. So try to simplify this down to, if you can, simplify your fraction whole component, like the 2/3 or anything like that, if you can. And then you want to have each one of your variables, your x, y, z, a, and b, you just want to have one of them available. And then you want them to just, like, if you just want one of them to a power, that's another rule of simplifying. And then you want to make sure that your exponents are positive. So those are all the things you want to make sure. You just want to make it look as nice and clean as possible. Pause this for a second and work on these. So I have 2 times x times y over 3z to the power of 5. So according to my rule, we're going to have 2xy to the power of 5. And then we're going to have 3z to the power of 5. That goes to the top and the bottom. Well, then this 5 distributes across the product. So we have 2 to the power of 5, x to the power of 5, y to the power of 5. And then on the bottom, same thing. We got a product raised to the power of 5, so this distributes. So we get 3 to the power of 5, z to the power of 5. Okay, well, I know what 2 to the power of 5 is, but 3 to the power of 5, I need to go find that quickly. All right. 2 to the power of 5, that is 32. And then we have x to the 5, y to the 5. 3 over 5, or sorry, 3 to the power of 5 is 243. And then we have c to the 5th. So this is what the simplified form would look like. And 32 over 243 does not simplify. So that's about simplifies that fraction is going to get. So as you saw here, all we did was that everything, because this is all products and quotients, everything got the power of 5. We can cheat here and do the same thing. Everybody is getting that power of 7. So x squared gets the power of 7. Y gets the power of 7. A to the 4 also gets raised to a power of 7. And b to the negative 5 also gets raised to a power of 7. So we got a power raised to a power. So x to the power 2 raised to the power 7. That is just x to the power of 2 times 7. And y had the power of 7. There was nothing else there. A to the power of 4 raised to the power 7 is a to the power of 4 times 7. And then we have b to the power of negative 5 raised to the power 7. So that's b to the negative 5 times 7. That's going to be x to the 14, y to the 7, a to the 28, and b to negative 35. Negative 5 times 7. My last step is I just want to turn this negative exponent to something positive. So that is x to the 14, y to the 7, b to the 35, over a to the 28. We're going to simplify exponential expressions. So like I said, I've been talking about these rules as we go along. An exponential expression is simplified when there's no parentheses up here. So we try to get rid of them. If there's a negative number, then we may keep a parenthesis, but we try to get rid of them if we can. No powers are raised to powers. Actually, you know what? That's when we can make all parentheses disappear. We can do that. No powers are going to be raised to powers. So you should only have a variable raised to a power. Each base occurs only once. And no negative or zero exponents will appear. Because remember, anything to the power of zero should just be one. So that will be just basically take care of itself. So once again, take a moment and pause and work on these two problems here. And then come back for your answers. All right, so we have 12 over 18. We have y and again, we have 12 x y to the 11, 18 x to the 5, y to the 8th, all raised to the power of 3. So I can distribute the 3 across first. I can simplify everything in the exponents first. Or the parentheses first. It's not going to matter. To make it easier to deal with all the numbers, everything in the parentheses, I'm going to simplify that first, then distribute this 3 across. So 12 over 18, both of those are divisible by 3, right? Yeah. No, 6. Both of them are divisible by 6. So that's going to simplify to 2 on top and 3 on the bottom. Then we have x to the power of 1 here and x to the power of 5. So this will be x to the power of 1 minus 5. And then we have y to the power of 11 and then y to the power of 8 here. So we'll have 11 minus 8. Okay, and I know it's a little silly looking, so I'll put that 3 in the middle so it looks less weird. This is just going to be 2 x to the power of negative 4, y to the power of 3 over 3, all this still raised to the power of 3. So I haven't dealt with that 3 on the outside. Simplify this one more time. This is 2y cubed. And then the x to the 4, I can move that down here. So it's x to the negative 4 becomes x to the positive 4 times 3. All raised to the power of 3 still. Now I can distribute that 3 across. We have 2 cubed. We have y cubed again. We have 3 cubed. And then we have x to the 4th cubed. So 2 to the power of 3 is going to be 8. We have y to the 3 times 3. 3 to the power of 3 is 27. And then we have x to the power of 4 times 3. So we have 8 y to the 9th, 27 x to the 12th. All right, and we can't simplify the 8 over the 27. That's already simplified earlier for us. And you might have done this a different way, and that's fine. This is just one of the ways we can do this. Okay, so B, same thing. Let's simplify everything in the parentheses first. Well, actually, let me do this the other way. Let me distribute the negative 3, and then we'll simplify. So like I said, I could do this rule first. I could distribute my power. That's going to give me 2 to the negative 3 times a to the power of 6 to the power of negative 3 and b to the negative 3. Then I'm going to have a to the 8 raised to the power of 3 and b to the negative 5 raised to the power of negative 3. So We'll deal with this here in a second, but let's combine what we can. So that is going to be 2 to the negative 3, a to 6 times negative 3. So this is negative 18. And then we have b to the negative 3. And then we have a, oops, a is going to be to the power of negative 24. And b will be to the power of negative 5 times negative 3 is going to be positive 15. Like I said, there's different ways to do this. So let's move all my powers, everything around, so everything's a positive power. If that's the case, this 2 to the negative 3 goes to the bottom. We get 2 to the positive 3. A to the power of negative 18 will go down here and become a to the power of 18. B to the negative 3 goes down here and becomes b to the 3. And this b to the 15 doesn't need to move, so, oh, sorry, we're not in b to the 15 yet. We got these ones moved. A to the negative 24, if we don't want that negative and then we want that positive, that's going to go on top and become a to positive 24. And then this b to the 15 will stay down here because that didn't have a negative exponent. It does not move. So now on top, we have a to the 24th and we have a to the 18th. So now we have a to the 24 minus 18. 2 to the power of 3 is 8. And then the b's, we have b to the 3 and b to the 15. So that's b to the 3 plus 15. So we should end up with a to the 6 over a b to the power of 8. And as I said before, you may have done this different ways. Hopefully we all came out to the same answer in the end, though. Okay, so scientific notation. A number is written in scientific notation when it's expressed in the form of a times 10 to a power of n. Now, n could be a negative exponent or a positive exponent, but usually it's going to stay an integer of some sort, where the absolute value of a is going to be greater than or equal to 1. That's what we want, and less than 10. So we want it to stay in that range there. And like I said, n is going to be an integer. So a can be a decimal, though. So scientific notation is used to express extremely large or extremely small numbers. For example, the speed of light is approximately 670,616,629 miles per hour, which is a very large number. So what we'd like to do, we're going to take that number, and we know there's a decimal place here, right? We want to move that decimal place up here. We're going to take it and we're going to write, usually simplify it down to like maybe 2 or 3 places. So this is really just going to be changed to 1.7061629, and we'll simplify here in a second, times 10. So every time we move this decimal place, that was a 10 that we had here. So this was 110, 10 squared, 10 to the third power. So if we count this is 1, 2, 3, 4, 5, 6, 7, 8. So we're going to end up with 10 to the power of 8. Now, like I said, we usually don't keep this whole long number here because what we're trying to do is condense this. So what we probably would do is take this and go, well, that's close to 6.71. So 6.71 times 10 to the 8 miles per hour. So that is how we use scientific notation. So essentially what we did here is, like I said, number, here we were just rounding it first, and then we moved that decimal place. So really what this comes down to is that if my decimal place here is moved up here, what I have is 6.71 times, get all these zeros here, 1, 2, 3, 4, 5, 6. Okay, make sure I had enough. Turns into 100 billion. And so instead of writing 100 billion, we just rewrite that as 10 to the 8. We want to convert into scientific notation. So write each number in decimal notation. We're going to convert. So if I'm in this notation and I want to go back to decimal notation, I have a negative 2.6. And what I want is, I want to times it 2, 3, 4, 5, 6, 7, 8, 9. This 10 to the power of 9 means I have 1 followed by 9 zeros, so I'm multiplying it by a billion. So another way to think about that is that I have negative 2.6, and I need to put behind it 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Oops, not 9 zeros, 9 decimal places. Do that one more time. I need to put behind it 2, 6, 1, 2, 3, 4, 5, 6, 7, 8. Add one extra zero there, because all we're doing is that when I multiply these together, this is going to move this way 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. If I have 3.017 times 10 to the negative 6, second here. Now, if it's a negative 6, I'm going the other way. So when we have this means I have 10, or I have 1 followed by 9 zeros. This means it's something a little different. This means I have 3.017 times, I'm going to have that 1, but what I have, 1, 2, 3, 4, 5, it tells me that the 1 is going to be, or where my decimal place is going to be in response to this 1. The 1 should be 6 decimal places out. 1, 2, 3, 4, 5, 6. Okay. If we multiply this, what you're going to end up with is this decimal place is going to be moving this way 1, 2, 3, 4, 5, 6 times. So if it's a negative 6, we move the decimal left 6 places. Here we had a positive 9, we move the decimal right 9 places. So when it's positive, we're moving to the right and we move the decimals many places we said. When the decimal, or when it's a negative exponent, we move to the left and we move the decimal that many places. So you can think of this as telling you how many decimals, how many decimal places you're moving the decimal point. And if it's positive, we move to the right. If it's negative, we move to the left. So in the case of speed of light, if we had that number 6.71 times 10 to the 8, we move the decimal place 8 places to the left, so we'd have an exponent of 8. In the case of the gravitational constant, if I wanted to go backwards and write that, like I said, in this case, that decimal place went 1, 2, 3, 4, 5, 6, 7, 8. Like I said, that's how we get 10 to the 8. If I have the gravitational constant, we would move this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And since we had to move backward this way, we'd say 10 to the negative 11. So when you go the other way, you take the big number and you convert it to scientific notation. If I have to move my decimal to the right, then we get a positive exponent. If I have to move my decimal to, sorry, if I move my decimal to the left, I get a positive exponent. If I move it to the left, we get a negative exponent. So we want to convert the following from decimal notation to scientific. The best way to think about this is that positive powers mean big numbers, negative powers means we have small numbers. So we need to take this. I know it's going to be 5.21 because I want to make sure that basically that decimal place is going to go right here. So it's a number between 1 and 10 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9. Here, we got a negative, we're going to put that decimal right here, negative 6.893. And to get here, that decimal had to move 1, 2, 3, 4, 5, 6, 7, 8. So times 10 to the negative 8. Because in this case, we got a small number, we got a decimal. Okay, so you know this in calculators, many calculators have a different notation for scientific notation. So if you have some big numbers that you're dealing with, you might see this. Instead of 6.71 times 10 to the 8, some calculators might show you instead 6.71 e to the 8. So if you see that e, it's just telling you it's times 10 to the 8th. If we had the 6.673 times 10 to the negative 11th, your calculator might show 6.673 e to the negative 11, which we know means it's times 10 to the negative 11. All right, so our last worksheet problem, convert the following into scientific notation, and then convert these following, so they're no longer in scientific notation, they're in decimal notation. All right, so we have what is this? 19,600,000,000, and we want to convert this to scientific notation. So we're going to put our decimal place here. So we're going to get 1.96 times 10 to the, so if it was decimal point was here, we moved 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be 10 to the power of 10. Here, we're going to put that decimal place here so we can get a number that's between 1 and 10. So we get 8.112 times 10 to the, I move my decimal place, 1, 2, 3, 4, 5. Negative 5, represent that decimal. So here, we're going to move, we got 4.81 times 10 to the negative 8. So we have our 4.81, and we're going to make it a number that looks like this, right? So we're going to move to the left 8 places. 1, 2, 3, 4, 5, 6, 7, 8. So it's 0.1, 2, 3, 4, 5, 6, 7, 4, 1, 8. So we'll get rid of that decimal. Here we got 6.5, and we have 10 to the power of 5. We're gonna make a bigger number, so we're gonna move to the right 5 places. So we'll go 1, 2, 3, 4, 5. So now my decimal can go away.